All right, so in the ionic bonding, there's a couple of things that you should know. So remember, what's an ion? Charged atom. It could be positive, it could be negative, doesn't matter. It's a charged atom, right? So there's a couple of things we're going to do with the charging. We're going to talk about the types of bonds. So in this molecules section, we're going to learn about the types of bonds. So the first type of bond we're learning about is the ionic bond, and then we're going to learn about the covalent bond, followed by the hydrogen bonds and van der Waals forces and things like that, ways that the atoms can bond together. So we're no longer talking about atoms as singular, we're talking about atoms interacting, okay? So we're going to talk about them going together. So you need to remember valence electrons, Lewis dot diagrams, cation, anion, and why they change their electron numbers by ionic bonding and how ionic bonding actually works. All right, so a Lewis dot structure represents an atom's valence electrons. So I need you to write this down. Make sure you have it in your notes. Make it really, really obvious to yourself. Change the color, whatever you got to do. Valence electrons are the electrons in the outermost shell. You should have already known this. It's not all the electrons in the molecule. It's just the ones in the outermost shell. It's just the ones that are the furthest from the nucleus. It's not counting any of the inner ones because the inner ones are all paired. If you remember the sp, d, and f, and when you're filling up those electron orbitals, it's the ones that are at the end. It's the last set of orbitals because those are the ones that are involved in bonding. None of the others can be involved in bonding because they are full. They are together. They are already paired. All right, so the valence are the ones in the outermost shell. They're whatever is the last set of orbitals. All right, so Lewis dots. Each dot represents an electron. Maximum counts are 8 valence electrons. So there's a maximum count of 8 possible electrons around an atom, except for helium and hydrogen, which are the only 2 atoms which are in the first energy shell where they're full and their valence energy. So they're full with 2 because that's an s orbital, right? So all the others will be full with 8 valence electrons. So dots are the electrons, and the electrons are the same charge. So if they're the same charge, would they be next to each other? Think like magnets. Do I put 2 of the same next to each other? What do? They repel, right? So that's what happens here. 2 of the same charges makes them repel. So they only pair up to the last second. They don't pair up until the end, all right? And that's wise because they have the same charge. All right, so in order to draw these, you're going to need to put the element symbol in the middle. Remember, there is an important way to write this. The first letter is always capitalized. The second letter is never capitalized. If you capitalize that second letter, then we're not going to get it right because it's two letters for 2 elements. So you capitalize the first, never the second. They are all 2 letters or less, all of them. No longer do we have like the uninotium. We now have everything named on the periodic table, so we don't have those 3 anymore. All right, so you can put the symbol in the middle, count the number of valence electrons. So remember the valence electrons, we can do this with the periodic table, right? So on the periodic table, you remember that the electrons are similar to the group numbers. Group number 1 elements have 1 valence electron. Group 2 have 2. We skip the transition elements because they change. They have some weird things going on. You know this because you have done the D shell orbitals and they do some weird things. So we skip the short rows. When you get to 13, you take the 1 off, there's 3 left, right? So there's 3 valence for 13, there's 4 valence for 14, 15 is 5, 16 is 6, 17 is 7, and 18 is 8. You see that? Some of you on your test, this is why we're doing a little bit of a review, because some of you on your test obviously can't remember what the 8 valence electrons are about. So that's why we're reviewing this section. All right, so when you put these on, you have to figure out which one you're doing and how many valence electrons it is. So let's say I'm going to do boron. Boron's number 5. You see it there? All right, so boron's number 5. I'm going to put boron. Oh, I can't. Oh. Or I'll do it over here. All right, so I'm going to put a B in the middle because I put the symbol in the middle, right? And then I got to figure out how many valence electrons we have. So how many valence electrons is in boron? He's in group 13, so how many would he have? 3. All right, when I put them on, this is the order in which they go in. They go clockwise twice, basically. All right, so the first dot goes where the 1 is, the second dot goes where the 2 is, the third dot goes with 3, and so on and so forth, right? So you're going to start numbering around the top and go around like a clock. So I'm going to put first electron, second. It should be, those are numbered wrong. Should be second on bottom, third, fourth. The reason why I put it on bottom, I would put the second down where the 3 is. And the reason why I do that is because they're going to go as far away as they possibly can. So I would do 1, 2, 3, 4, 5, 6, 7, 8. They go not like that. 1, 2, 3, 4, 1, 2, 3, 4. And the reason why is because they're going to be as far apart as they possibly can be. They don't pair up till they absolutely have to because they are the same charge. And even when they're paired up, you already know they're going to change spins, aren't they? One's going to spin up to down, one's going to spin down to up, right? Backwards from one another. Because they're going to be as opposite as they possibly could be, even though they're not that far off. So you can do any of the elements this way. The electrons we're going to practice on Friday, how to do the Lewis dot structures. We're going to come back to that once we're going to watch it. We're going to do that in a second. All right, so if you have calcium, it has 2 valence electrons. Remember that the valence electrons are the last energy shell, so they're the last one here. So when you're going through, all of these are not involved in any bonding. None of them. The only ones that are involved is the last energy shell. In this last energy shell here, you wind up having 4s2. Calcium, how many does it have? 2. See it? It's in the second group. It has 2 electrons left in the outside. Is everybody following me? All right, so 4 is the highest shell. So there's 2 electrons in the 4th energy shell. It has 2 valence electrons. How many to make it happy in this that it's going to need? He has 2. Is he going to give away those 2 or is he going to gain what? 6? He could gain 6, but that's a lot, right? It'd be much easier to lose 2. That's why he's in that group. What group is he in? If he's calcium, what group is this? Alkaline earth. Alkaline earth. A lot of you don't remember what those are. Alkaline earth are highly reactive because they're giving away electrons, right? Shoving them away. They're not quite as reactive as the alkali booms, right? But they're giving those electrons away. They readily react with which group? Who needs to? So group 6. All right, so he's going to act with these oxygen group, right? So you have to be aware of what these go through. So you have neon. All right, so neon has 2 is the highest shell number because you wind up with 2s2, 2p6. See how the 2 is the same shell? You see it? So how many valence does he have? 8. A lot of kids mix this up and say 6. It's not. It's actually 8. You see why they're both on the same energy shell. They're in different orbitals, same energy shell. That's what the test was on. You've got to know all the different quantum numbers and how to put them together so we can move on and apply this knowledge. All right, so this is one shell, and it has 7 total. So, or I'm sorry, 8, because I can't count. So you'd put your dots on here, and you wind up with all paired electrons. Can he bond with anyone? Is there space to bond? No. He can't bond with anyone because everyone is already paired. He has 4 unpaired electrons. He can't do anything. That's why he's a noble gas. That's why he doesn't bond with anyone. A lot of you missed that on the test. Why do noble gases not react? Are they found in nature alone or bonded with something? Alone. He can't bond with something. Not unless you strip one off, right? So you're going to wind up having 8 valence electrons. That's why he is found alone in the world. All right, so the octet rule, rule of 8, right? Oops, I went too far. All right, so atoms gain, lose, or share to have 8. That's going to be important. Why, though? Like, why 8? Why? Why do they gain, lose, or share to make 8? So they can be stable. What does stability mean? Come on. Y'all the smartest minds we got here. What does stable mean? If I say something stable, what am I saying?
Good.
It's perfect.
That's already steady, like.
So what is unstable then?
Not good.
No, I just say not stable.
Not stable, obviously, but what does it mean if I'm a molecule and I'm not stable?
That means we got an electron.
You don't have it, but what would it mean though? It's reactive, highly reactive, right? But it's going to be reactive on its own, causing, like, it's not going to be around long. He will want to bond no matter what. If he's not stable, he's probably going to be radioactive. Radioactive is an element trying to become more stable on its own. It's giving off radiation. All right, so an easy way to remember is remember the group numbers. This one has 1, 2, 3, 4, 5, 6, 7, 8. That's what we talked about before. Do not count the little transition metals. Those you have to actually do the, you have to all the way do the complete electron configuration because they are different. They don't follow the rules. Yeah, they're very unique. So you would have to actually do all the electron configurations out for all the transition metals in order to figure out how many is in valence because they'll be all over the place. They're a little different. So generally when we ask you these questions, we're only going to deal with the ones that have a numbered valence electron. Otherwise, it would just be too much work. So don't worry about the transition as much. All right, so remember that an ion is an atom with a charge, right? So it can be positive or negative. As is 2 options. Cations are positive or negative. Positive. Anions are negative. There you go. All right, so when you're talking about potassium, this is my full electron configuration of potassium. On the test, you were asked about orbital notation. If you can't remember that, it's not that bad. A lot of people, literally every person in this room except for 2, 1 because he didn't take it, and 2 because he aced it. But you've got orbital notation are the boxes, people. You've got 1s. Oh, 2s. And then you have the 2p6, right? Which is 3 boxes. This is, yeah, I know. Remember, Hund says that you have to put 1 in each box before you can go back and pair them up because the like charges repel. So all you had to do was that goes up. He's filling the shell before he goes on. He's filling the shell before he goes on. He's going up, 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 down, down, down. That's orbital notation. Hence the 1s2, 2s2, 2p6. Y'all remember this? I know you wasn't thinking. Y'all made me pull my hair out. It's like, I know they know this. I know. So potassium. Potassium, what is it? It's a 4s1. So where on the periodic table would I immediately know to look? Group 1. How does she know that? Because first off, she knows it's an S, and she knows there's only one of them, so she knows it's got to be in group 1. Don't waste your time on looking on a periodic table. Think your way through it. Work smarter, not harder, right? All right, so potassium, we know because of the 4s1 that it's got 1 electron. So if potassium can give away that 1, it'll have 8. That explains why potassium is so reactive. Again, another question y'all screwed up. What about a group would explain the reactivity? Well, if he only has 1 and he needs 8, he's gonna throw it away really fast. That's so he can be more stable, because he is more stable with none than he is with 1. All right, so potassium has 19 protons, 19 electrons. It loses that 1 electron, right? So what is it gonna look like now? Because it'll have 18. So a stable potassium, am I ever going to find potassium in the world as 19 electrons? Not for very long, because what's going to happen if anything gets near it that it can bond with? Instantly bonds, right? Instantly does an ionic bond. You rarely see these ions in the presence by themselves. You know this because we burnt them. Remember the flames that are really pretty colored? We burnt them. We burnt these potassium salts. We burnt them. That way you could see that the ions are not around very long. You know these things, you just didn't think about them. All right, so the potassium ion always has a charge of +1 because it has less electrons than it does protons, so it's going to be a +1. We don't write the 1 because just like in math, 1's understood. But you would put a plus sign there. All right, so let's look at this one. So the potassium ion, though, if I did the electron configuration, it looks like this. So if I ask you to write the electron configuration for an ion, which was also on that test, it does not look the same as an electron configuration off of the periodic table, does it? Actually giving away an electron, right? So it would go down and back 1 on the periodic table from what you think it is. So the periodic table of the potassium ion looks exactly the same as which element? Gotta go backwards. What is it? Come on, y'all smart. Here's potassium. Which one would have been matching? Argon. She's right. See why it has 8 valence electrons and he's happy now? All right, so you wind up looking like this. So if I do the Lewis dot, your potassium ion is fully filled electron shell on its highest one, right? All valence electrons are there on the ion. If I take away that plus sign, this is all wrong. So I'm kind of trying to do 2 things in one here. I'm trying to review with you and then add some more. All right, so fluorine. Fluorine, what does it do? It gains an electron, right? So if it gains 1, so you've got fluorine over here. He gains 1, he can be stable. If he gains 1, is his electron configuration going to stay? Predict, what's his electron configuration going to look like if he gains 1? 2p6, right? You already know this. So if he gains 1 electron, fluorine's going to gain an electron. What's his charge going to be? -1, man. I don't know what your problems are. All right, the fluorine has a charge -1, but it's more stable. That's why things bond, okay? Why does it bond? To become more stable, so it's less reactive. All right, so if fluorine ion has the 8 valence electrons, if I don't include that negative sign, is it correct? If I don't put this negative sign, is that correct? No, it's not. It'll be wrong. You know positives are cats, negatives are ants. I don't have to go over that. All right, so I like to explain ionic bonding with a little love story. I always do this because it's easier to understand. I know, it's weird. All right, but little Mr. Sodium and Miss Chlorine are going to form a bond. All right. So if he is 3s1, he only has one outer shell electron and really wants to give it away, like Pepe Le Pew wants to give it away. Do you guys still do Pepe Le Pew? Probably not. No, about the skunk who's like in love with everybody.
No.
You know, this cartoon
What?
dude.
I don't know.
The stump?
The skunk.
Oh.
You don't remember Pepe Le Pew? It's like Looney Tunes. Like
That's
old.
probably back in the day.
Yeah, it's like back in the day when I was young. All right, but he like really wants to give it away and, you know, have a relationship, and everybody's like, nah. All right, but he's got one little dot here and he wants to give it away. He doesn't want to hold on to that dot. So what's going to happen is little Miss Chlorine's over here. She's all lonely. She has 7 electrons. She really wants somebody else. She's kind of brokenhearted. So what's going to happen is they're going to come together and they're going to share. No. What are they going to do? All right, he gives her his electron wholeheartedly. Complete it. Take it. I don't want it. She has a full 8. He has none around him, but he winds up having a full shell. Do you see why he has a full shell too? Because he lost the 1, so he gets the noble gas configuration. So he's technically full as well. Even though he lost 1, he becomes full. Does everybody understand that? That's why I say it's a relationship. He lost his heart, but he gained a whole. I know, it's so sad. Stupid. All right, but why do they do that? Because a couple is more stable. Hilarious. I know. It's always a metal with a non-metal. You noticed? Always. Even when we're in our lab and we're doing our reactions back there, all of the stuff that you were doing with the flames and a lot of these excitable electrons in that excited electron lab, did you notice that it was always a metal something with a non-metal something? That's because they go together. And what they form is called a salt. Mm-hmm. Not the salt, a salt. A salt is any metal ion attached to a non-metal ion. That makes a salt. Table salt is not the only salt. It is just one of many. Anybody here is like, usually it's like dads, but anybody have like high blood pressure in their family and they can't have salt, or high diabetics? Some of them can't have a lot of salt because it messes with the blood pressure. So they give them food that has been salted with a different salt, and it's a magnesium salt. Still gives you the taste, but it's not going to raise your blood pressure as much because it's using a different ion combination. There's many salts. You just know the one salt, sodium chloride. That's table salt. That's the one you just happen to know of. But it is just any metal that is attached to any non-metal ion will generally make a salt. All salts are crystals. You know this because you've seen table salt. They're little crystals. All right, and the way that these bonds are held together is because they give their electron completely away or take the electron completely in, one or the other. So they can receive those full electron shells. Everybody get that? So even though sodium lost an electron, he's still a full shell. And they're held together by opposite charges. All right, so we're going to actually write these on a little piece of paper. I'm going to take them instead of putting them in the inbox. But you're going to answer these questions. You have them on your screen, so we don't have to wait on me. I want you to write them on the bottom of these notes somewhere. When you submit them, I'll check them on there. So you just put 1 through 8 on there. You don't have to rewrite the questions. Just put 1 through 8 on there somewhere and answer them. Mm-hmm.
Put it on the back.
Mm-hmm.
We only got
Not 8. What did I say? 8? I meant 4. Sorry. I don't know why I said 8. I'm thinking valence electrons.